So should we start or start
That's
the
great.
intro?
Well,
Yeah, yeah. Yeah, we can start the introduction slides and waiting more people. Yeah. Yes. So hello everyone. Welcome to the AGN SIG, the dissertation Jamboree, the series talk. So it's a 3 day start from today, tomorrow, Wednesday, and Thursdays. So I have to thank everyone, all the speakers to contribute their research work in their PhD and present all the results to us. So I just thank all the speaker list is here. Um, Today we have the first day we have two speakers. The first is Julian Falcone, come from the Georgia State University, and she was talking about the spatially resolved multiphase analysis of AGN-driven feedback and outflows in NGC 3227. And the second speaker will be Steve DiKerby. Yes, and he comes from Michigan State University, and he will focus on the X-ray things. Topic is M31, M32, and Sagittarius A as active galactic nuclei in X-ray. So I still have some advertise about this month event. We still have the AGN coffee next week. So this month will be 7 May is 1 to 2 Eastern time. We have the Asian Coffee discussion group in the Discord. So if you haven't participant the Discord group, you can just scan the QR code right now. Um, and we have post some interesting paper in there if we can have a brief discussions in every monthly agent coffee discussion group. Yeah. And we also have the vision series talk on 26 May. It will be at 1 to 2 p.m. at the same times right now. And this month we'll have a Stephanie, and she was talking about the galaxy evolution and aging something, and she's now in the NOR lab. So this is the advertise of this month. So I stop sharing and give the so so give the first speaker, Julian, you can share your slides right now. Yes.
Okay, thank you so much. So I'm just going to, all right. Um, can you confirm one more time that it is working properly?
Yes.
Amazing. Okay. Well, thank you so much for the introduction. Yes, hello, my name is Julian Falcone, and I defended my dissertation about 10 days ago. So we are hot off the presses. And I'm really excited to be sharing my work titled Spatially Resolved Multiphase Multi-Scale Narrowline Region Outflows in the Seyfert 1 Galaxy NGC 3227. So, just to get us all on the same page, we know that gas accretion to the supermassive black hole results in the expulsion of gas in the form of outflows, which we can see here with this diagram on the left. Now, these outflows propagate along a biconical or hourglass-like geometry that ionizes the narrowline region, which again, we are seeing here from this diagram showing how these outflows are heating up the gas in the disk. So these narrowline region outflows result from the ionization and subsequent removal of the cold molecular gas reservoirs that are located in the central regions of the galaxy. And so that forms the basis of how we're going to be studying these outflows, is in relation to these cold molecular gas reservoirs. So my work in particular has focused on the nearby Seyfert 1 galaxy NGC 3227. You'll notice it has a snazzy dwarf elliptical companion just up north of there. And the reason why this is such a great galaxy to study is because it is so nearby, we can really probe into the innermost regions around the nucleus. These are sub-arc second resolution measurements that we can analyze and interpret how the feedback mechanisms are operating in these innermost regions and subsequently how they impact the galaxy on a much more global scale. So my dissertation work was broken up into two general studies. The first was asking how can we characterize the orientation and the extent of the multiphase outflows we observe in NGC 3227. And in this case, we're primarily focusing on characterizing the kinematics of the outflows and of the gas. And the second study is building off of that and asking what are the mass outflow rates for the multiphase gas as a function of distance from the supermassive black hole. So once we have a better understanding of the kinematics from the first study, we can use that to better understand the expulsion of the gas in a spatially resolved study, which is the second project. So my work has focused on both large and small scales. So we're focusing on both the entirety of NGC 3227 and also this innermost nuclear region. And what we're seeing here on the right with these contours, so this is just the O3 flux, which is heating up, which is very visible in this region that highlights the narrow line region. And in terms of some of the instrumentation that we've used to complete the study, we've used a combination of Apache Point Observatory's Cosmos spectrograph, so that is able to span pretty much the entirety of the galaxy, as well as some data from the Hubble Space Telescope Wide Field Camera 3. And that is the WFC3 data. That's how we were able to get that O3 emission on the right. We also utilize HST STIS data, so that's what you see on the right in green. And you can see how the green slits overlay on top of much of this O3 emission. So they are oriented in relation to the narrowline region to pick up as much emission as they can. So this is what allows us to get really high resolution data close to the nucleus. We also utilize some NIFS data to get some near IR measurements and also ALMA data to better understand the cold molecular gas at this area. So once we have all of our instrumentation that we're applying on these different scales, what we can then do is because this is primarily long slit spectroscopy or IFU spectroscopy, we can isolate the spectra at each distance, at each point along the slit, and see how exactly the kinematics are behaving at each space. And so in order to analyze the kinematics of the spectra, we use a tool called the Bayesian Evidence Analysis Tool, or BEAT. And what this does is this helps us to deconvolve the rotational and the outflowing motions. So for example, if you have an input spectrum like we see below, where we can very clearly see the H alpha emission with the nitrogen 2 emission on either side, what we can then do is utilize BEAT to fit our spectra. And so you'll see here that it can recognize that this is a two-component fit, which we see here from the red and blue components for each of these emission lines. So it's recognizing that there are two distinct kinematic signatures observed in the spectrum. And also, because this is a Seyfert 1 galaxy, it can also fit the broadline region. So that's what you're seeing at the bottom with this olive curve that spans for this entire little section here. So once we're able to use BEAT on all of our data, and then from there we can get a handle of the kinematics, great. So we have the kinematics. Now we can actually interpret what is going on here. And so from the kinematics, we're able to better classify where we can observe outflows. And so what we're seeing here is data from one of the Cosmos slits. And so you can see its positioning on the right in relation to the galaxy, how it runs along the major axis and even intersects NGC 3226. What you're seeing in green is a rotation curve of the galaxy from CO data. And in blue are the resulting kinematic points that we obtain after using BEAT and solving for the velocities of the gas. And so what we can observe is the fact that there is a really strong deviation of the data from the expected rotation curve out to about 700 parsecs. And so this is just one example of how we're able to see the difference between the expected kinematics of the rotation curve and the observed kinematics of the outflows and classify where these high velocity outflows may be present. The importance of classifying these outflows and determining where they exist is that we can use them to better understand the orientation of the outflowing bicone. So you'll remember that at the beginning, we showed the figure of the biconical outflows emanating from the supermassive black hole. And one of the main goals of my study was to better constrain the orientation of the outflowing bicone for this galaxy and in such a way that it can be replicated in other nearby AGN. And so I don't really have much of the methodology present here because of the constraints of the time limit. But what we briefly did in order to obtain what we have on the right, which is the best fit model of the bicone orientation for this narrow line region, is we fit hundreds of thousands of kinematic models that we then compared to our STIS data and found that wherever the kinematic models best matched the data, what led to what was the likeliest model of the bicone. And so from here, we were able to obtain a model of the bicone that helps us to better understand exactly how the outflows are likely propagating. And finally, for this project, once we have an understanding of the kinematics, once we have an understanding of the bicone, what we can then do is better understand how the outflows are being driven. So what we still want to better understand with studies like these are what are the primary driving mechanisms of feedback for especially lower luminosity AGN, of which this is falls within that sample. NGC 3227 is not the strongest AGN. And so in order to try to get a handle on what exactly is going on, we test out the efficacy of radiative driving as a mechanism, which basically asks what happens if you balance the outward force of radiation pressure with the inward pull of gravity. And how do these two things balance out and give us a sense of whether this can correctly describe the kinematics of the observed gas. So yes, as I mentioned, we have the opposing forces of radiation pressure and gravity using a formula dependent on the bolometric luminosity. And so what we're seeing here on the right are trajectories of gas depending on, as a function of this radiative driving. And so each of these black curves shows the modeled trajectory of gas depending on a launch distance. So gas that is launched from much closer to the center is going to go further and faster than gas that is launched a little bit further out, which is, again, what these black curves are showing. In red, these are our observed kinematic data points, where we're utilizing the kinematics that we solved for in the Cosmos data and the STIS data. And so from here, what we can see is some of these higher distance and higher velocity points. If you trace that backwards, this means that this gas was likely launched from the innermost 2 to 3 parsecs from the supermassive black hole. Furthermore, something I want to point out is what we call the turnover radius. This is the distance at which acceleration turns into deceleration. And the reason why this is critical for the study is that the way we confirm the likelihood of radiative driving in the system is by comparing this modeled turnover radius that we see here to the observed turnover radii that we obtain from our kinematic models. And by seeing whether or not they match up on a one-to-one ratio, from there we can confirm that radiative driving is effective and likely the driving mechanism for these outflows. So I've kind of skipped to the end in that way, and that I wasn't able to really show you a lot of that process. But what we are able to see here is that radiative driving is likely the effective means of driving these outflows. And this is crucial because most AGN are on this lower luminosity scale. And so by better understanding how AGN like these are able to drive their outflows, we can use that on a larger sample to better understand whether these feedback mechanisms, how they're behaving on these other targets. So that was primarily my first study. And as I mentioned, my second study builds off of this and moves into the realm of spatially resolved mass outflows. So what we're seeing here on the left is that historically, most studies about AGN-driven mass outflows have been represented by a single global value. So on the x-axis, you have the mass outflow rates for cold molecular gas. On the y-axis, you have mass outflow rates for ionized gas. And each of these points is a different target where a global value for both of these things has been computed. But we know that in reality, this is not the case. We know that based on recent studies by Rowalski et al., that if you have the mass outflow rates and if you can compute spatially resolved mass outflow rates for nearby targets, you'll see that there is a lot of variation as a function of distance. And therefore, these values can't really be accurately represented by just a single global value. So my second study has taken this ideology and asked a couple crucial questions as it relates to NGC 3227. First, it asks at what rates are various phases of gas being evacuated from the narrowline region? And second, how do these evacuation rates vary with distance from the supermassive black hole? And so in order to perform this study, we used primarily the ALMA data, which I hadn't really mentioned in the first study, but it was still kind of there for this target. And again, we see on the right, we have our O3 data that we used a lot for our first study. So we have our cold molecular gas and we have our ionized gas. And what we do is we divide these data into slices of around 11 and a half parsecs, which is the resolution element of the WFC3. So this is basically as small as we can get. And by performing this study, this represents among the first spatially resolved multi-phase studies of mass outflows. So what we've seen in the past are multi-phase studies with global values of the mass outflow rates or spatially resolved mass outflow rates of a single phase. Here, we're really looking at both spatially resolved and multi-phase studies. And in order to do this, we create cloudy models to calculate the gas masses for the ionized gas. The way that we go about doing this is first using our Cosmos data, we calculate O3 to H beta ratios along one of our slits. And this is important because the O3 to H beta ratio traces excitation, which depends on density. So this helps us to say that if the amount of mass that we observe depends on the amount of light we see, well, the amount of light we see depends on the excitation, and that depends on the density. In particular, we utilize two parameters, the ionization parameter U and the hydrogen number density NH. And so if we can produce cloudy models varying in these two variables, and these models produce their own O3 to H beta ratios, we can use our data to solve for U and NH at each point. And in particular, there's not a lot of equations here, but the main one to keep in mind is this one, which shows that these quantities are directly related, the ionization parameter and the hydrogen number density. And critically, they depend as a function of R, the distance from the AGN. And so the way that we go about solving for NH and U is if you look here with this middle plot, each of these three curves shows a constant density, a constant NH. And so if we were to example mark some random distance, let's say about 1.5 arc seconds, each point on each of these curves, you input that R, and then that way you can solve for log U by just looking downwards, and you can see the corresponding O3 to H beta ratio. So once you just have once you have the density, once you have the distance, you can solve for U. The dashed line that you see in the middle is the observed O3 to H beta ratio that you see on the left. You can see it's around 10 or so. And so by looking at where the observed O3 to H beta ratio is closest to the model O3 to H beta ratio, we can then solve at the most likely values for the density and the ionization parameter. So for this example, you would choose that orange curve, which has a density of around 10 to the 3 and a log U of around -3. So that was just for one distance, and we repeat this for all distances along our slit. And what we're able to then arrive at is a spatially resolved relationship between for the log U and the log NH values, which again shows that there's a lot of variation in these values, and they cannot be represented by just one value if you want to accurately calculate the ionized gas masses. So once we have the ionized gas masses, then we can go about calculating the ionized gas outflow rate. And we see that the peak mass outflow rate reaches about 20 solar masses per year at approximately 80 parsecs. And you'll notice that there's a stark difference between the northeast side versus the southwest side. The southwest side seems to drop off precipitously, and that's likely just because there is a very thick dust lane directly to the southwest of the AGN. That's why for the O3 image, you can barely see anything to the southwest there. And so you'd expect that if that dust lane wasn't there, you would see a pretty fair amount of symmetry. So we can repeat this process in terms of calculating the mass outflow rate of the CO data, the cold molecular data. And again, we're seeing outflow rates on the order of around 15 solar masses per year. And again, we're seeing high levels of variation between the data as a function of distance and just showing how important it is to calculate these spatially resolved mass outflow rates when possible. So finally, what we can do is use these data to estimate the how the cold molecular gas reservoir is depleted and on what timescales this occurs. And this is important because the molecular gas serves as the gas reservoir to fuel the ionized outflows. So by understanding how that reservoir is depleted, we can better understand the timescales regulating the AGN activity. So we do this in a couple of steps. The first step is by calculating a depletion timescale, which asks how long it takes for the molecular gas in the reservoir to become ionized, and then subsequently, how long it takes for the gas to move outwards from its current location to the edge of the outflows. What we're able to arrive at, and this is really the important plot here, is this evacuation timescale, asks how long it takes for the gas to be ionized and pushed outwards to the edge. And I know that there's these different legends here, these different colors. What we mostly want to focus on is understanding these values as upper and lower limits of the evacuation timescale. And so what we can learn from studying this evacuation timescale is that these gas reservoirs can be evacuated on the order of around 10 to the 6.3 to 10 to the 7.7 years. The reason why this is important is because the average duty cycle, which describes the duration of continuous AGN activity, is approximately 10 to the 7 to 10 to the 9 years. And so what this does is by showing that these timescales are fairly comparable, it shows that these AGN-driven outflows are effective in clearing the inner few hundred parsecs of NGC 3227's gas content. And so what this does is show outflows as being extremely important regulators of the feedback processes in this target. And in the future, what we would like to do is replicate the study on other nearby targets to better understand whether this is whether we can replicate these results or whether the efficacy of outflows depends on various features such as mass and luminosity or even morphology. So I'll leave you with just the future of this project. Here's the most recent paper if you would like to see it. And thank you so much for your time. And I'll take any questions.
Yeah. Thanks, Julia. Very, very exciting. Let me react. Very exciting result. So, is anyone have questions to Julia? First, congratulate to you to pass the dissertations. So, I mean, in your defense, yes. So,
Thank
is
you very much.
anyone, if anyone has questions, can raise the hand. Oh, there's the questions posed in the channel. So from Kai Wen Zhang. So from the bands et al. 2023, I think they have the dynamical modeling to show the orientation of the AGN is around 30-degree. So do you have compared this result to your result?
Yes. Yes, so that was part of the findings for the first project. We did indeed compare to Benz et al. Because she was on my thesis committee. And so I wanted to make sure to be very thorough. And we found that the orientation, especially as it relates to the inclination, is within the errors of her results as well, with their results. So we did find agreement between our results and their results.
Okay. Yeah. So any other questions? You can raise your hand or post the questions in the chat channel. So Swara Ranvin Dennis. So there's a question from an observational perspective, what is needed to make a major progresses in understanding molecular outflow from AGN?
Yes, that's a great question. So I think that because of ALMA, we're able to get really in-depth data. So I think that for the most part, that we have the data that we need in order to theoretically make the conclusions that we want. And I think what's missing is how to determine basically you have the molecular gas, you have a sense of the kinematics of the gas, but you don't necessarily have an understanding of what portion of those kinematics are outflows, what portion of those kinematics may be attributable to a bar, may be attributable to other kinematic disturbances or other inflows. And so something that I would like to work on in the future, and that's actually what you see here with my second future of this project, is helping to develop methodology that helps to sort of apply the beat methodology of deconvolution. So we've applied it primarily to our ionized gas, but figuring out how to apply it to molecular gas so that we can deconvolve rotation versus outflows versus any other motions that may be at play. Because for the most part, when people have reported outflows, it's been a little general, just based on kind of general motions and general kinematics. And I think it would be great to nail that down a little bit better so that we can better constrain the outflow kinematics of the molecular gas.
Thank you.
But
Thank
thank
you
you for
for
that
that
question.
answer.
Thank
Thank you for
you.
that answer.
So we still have time for one question. Is there any questions for Julian? If there is no additional questions, we can move on to the next speaker, Steve, talking about the X-ray AGN.
Thank you. Can you hear me okay?
Good.
So let me just share my screen. Can you see my slides?
Yes.
All right, great. I'm Steve DiKerby. I'm currently a postdoc at Michigan State University. And thank you for having me to talk about my ongoing work that I'm working on here at Michigan State. Today, I'll be talking about some very local supermassive black holes within our own local group of galaxies. And while none of these supermassive black holes reach the luminosities that we expect from active galactic nuclei throughout the universe, they do show a substantial range of variability and activity, especially in X-rays, that we can use to learn about the supermassive black hole and AGN paradigms. So that's why I've put active in suspicious quotations throughout much of this talk, just to keep that in mind. So without further ado, I'll launch into looking at how these local supermassive black holes can help us learn about activity near these objects. So Black holes themselves have a long history in physics and astronomy both. And only in the past 50 years or so have these two kind of independent lines of study come together. Black holes actually were first hypothesized over 250 years ago in the 18th century, back when we imagined light as minuscule bundles of material flying like rocks under Newtonian gravity. Some scientists posited that dense enough objects could prevent light from escaping. Obviously, today we understand the physics of black holes and supermassive black holes in the very successful Kerr and Schwarzschild metrics. And over the past 50 years, substantial evidence has built up astronomically for the existence of black holes and supermassive black holes. Naturally, we're an AGN interest group here, so we all know the observational signatures that lead us to believe that supermassive black holes, these incredibly unique and strange objects, can be studied in our universe, both dynamically and in their electromagnetic effects. Personally, I'm interested in the combination of these two different ways of studying black holes. First, as fundamental physics objects operating under general relativity, and also as astronomical objects in their own galaxies, how black holes and galaxies interact with each other. And Julian's talk that we just heard was a great example of that astronomical research. My research focuses on the most local supermassive black holes. Because these are so close, we can really get very detailed pictures of the activity around them, testing both our physics theories and our astronomical models for how supermassive black holes interact with the wider universe as a whole. So just to kind of set the stage, I want to move into the very local universe, the closest group of galaxies. What you see here is an artistic representation of the local group, about a 2 million parsec across region of space containing the Milky Way galaxy and our nearest neighbors, most prominently Andromeda in the upper left-hand corner here. The local group contains only those two big spiral galaxies, the Milky Way and Andromeda. It has a few medium or small sized galaxies, a couple small spirals, M33 in the Large Magellanic Clouds, a couple small elliptical galaxies, satellites of Andromeda, and then a whole bunch of dwarf and irregular galaxies. But what I want to underline one more time, and hopefully this doesn't make anyone run for the exits in this AGN session, is none of these galaxies in our local group host active galactic nuclei. If an AGN was present in Andromeda, for example, it would be one of the brightest stars in the sky and would have been known since historical times. While there are no active galactic nuclei in the local group, we have identified supermassive black holes in some of these galaxies, including our own. And the activity at those supermassive black holes is an interesting way to study them. So I'll start off right here at home in the Milky Way galaxy, and then we'll go further afield as this talk goes along. You might think it's very easy to look at the Sagittarius A star, our own supermassive black hole, but we live in the Milky Way, and that means we have to gaze through this thick lane of stars, gas, and dust in order to see the galactic center. I'm an X-ray astronomer, which means I can use telescopes like Chandra to create images of this innermost region. And with Chandra and other X-ray telescopes, you can see a mosaic here created by a grad student I work with, we can zoom right into Sagittarius A star on scales approaching 1 parsec in our galactic center and see the activity around the galactic center in particular. Sagittarius A star is in the middle of that bright portion over there, but that entire lump of high energy emission is not entirely from the supermassive black hole. There are other nearby objects cluttering up our view, to say nothing of the collection of molecular clouds and filaments you can see in the center of this image. We'll come back to those in a little bit later. So using telescopes like Chandra and NuSTAR, we can zoom in on Sag A star in particular. And in that way, we can learn that Sag A star is one of the dimmest known supermassive black holes in terms of Eddington ratio. The AGN that we're interested in here throughout the universe can approach the Eddington luminosity in terms of how much matter they accrete and then emit as high energy radiation. But Sag A star has less than a millionth of the Eddington luminosity. And that means it either is accreting very little matter or that accretion process is very, very inefficient, or possibly both. In terms of its radiation, it emits about a solar luminosity in X-rays and the rest in infrared and radio light. It's this radiation in X-rays that I'm interested in. You'll sometimes see supermassive black holes like Sag A star referred to as low luminosity active galactic nucleus. Personally, I prefer just putting scare quotes around the active and moving on like that as examples of activity around these. So when we look at Sag A star and X-rays, what do we see? And what can that teach us about accretion on the supermassive black holes as a whole? Sagittarius Star has a very low quiescent X-ray flux rate, but it also shows daily flares that are both an infrared and X-ray radiation. And these flares can elevate its quiescent flux by a factor of 100, by a factor of up to 100. This is work that a grad student here at Michigan State, Grace Sanger-Johnson, is working on in particular. One notable factor that we're currently working on is that the mechanism for producing these flares is not yet confidently known. And Grace here is using new star data to attempt to build multi-wavelength models for these flares. The two leading explanations are some form of electromagnetic reconnection close to the black hole, or mini tidal disruption events of something like an asteroid or a comet approaching the event horizon. Work is ongoing, and in the upper left corner, you can see how NuSTAR, hard X-ray data above 10 keV, is particularly important for discriminating between different emission mechanisms in this way. And we're using joint Chandra and NuSTAR observations in order to investigate these flares. One finding that I want to underline in this way is that Sagittarius A star, but despite having a very, very low quiescent X-ray rate, shows the same variability timescale and magnitudes that we see in other supermassive black holes, including some AGN. And in this way, we can link Sagittarius star, despite being certainly far below the Eddington luminosity, to AGN that emit much, much brighter. One particularly exciting flare that we're currently working on has two peaks, and one model suggests that this double-peaked flare could be gravitational lensing of material orbiting Sagittarius star. And in that way, we would be able to test general relativity at scales very close to the event horizon of this supermassive black hole. So using these X-ray flares, observations with NuSTAR and Chandra, we can build a bit of a timeline over the past decade, 20 years or so, of activity close to Sagittarius star. Sagittarius star is a very well-studied supermassive black hole in that way. But just a few minutes ago, I was complaining about all the other objects that obscure our view of Sagittarius star. We can also use those objects to learn even more about the history of high-energy emission from our supermassive black hole. Sagittarius star is surrounded by molecular clouds. About 5 to 10% of the total molecular gas in the Milky Way is within a few hundred parsecs of Sagittarius star. And these cold molecular clouds can reprocess and reflect high energy emission from Sagittarius star into our line of sight. Now, because it takes decades or centuries for light to travel from Sagittarius star to these molecular clouds and then get reflected to us, these molecular clouds can serve as, I like to think of them as time machines to look into the past and see how bright Sagittarius star was in the past. Now, obviously, these molecular clouds are all displaced along our line of sight, so there are big uncertainties about what the exact timeline is of Sagittarius star's activity. But it does let us constrain quite strongly the range of activity that Sagittarius star has shown. On the left here, you can see images from XMM Newton from Stell et al. In 2025, and you can see the bridge cloud has a wave front of light passing along it, projected along that direction towards Sagittarius star. In that way, it's a very dramatic demonstration of how these molecular clouds can test the past activity in Sagittarius star. Personally, I've been using CRISM to do this analysis. CRISM is a high-resolution X-ray telescope that has a resolving power of up to R is equal to 1,000. I know that sounds like kiddie change for optical and radio astronomy, but in X-ray astronomy, that's absolutely groundbreaking. It lets us do work like zooming in on the iron K alpha lines at 6.4 keV that we expect to see this reflected emission from Sagittarius star during. And by doing this, we can get the tightest constraints ever at this X-ray reflection model from Sagittarius star. In fact, we can model these lines with such precision that we can directly compare them to laboratory measurements here on Earth. And it makes this a very strong test of the 3D arrangement of these clouds and how bright Sagittarius star was. This episode of illumination that we've studied and just published earlier this year suggests that when this cloud was illuminated, it was seeing Sagittarius star about 100 years further into the past, emitting about 1,000 to 10,000 times more X-ray radiation than we currently see it emitting today. It's another piece of evidence suggesting that even in the recent past, Sagittarius star had substantially more high-energy activity taking place near it. And we're hoping to get more observations with CRISM to see this very narrow and strong line change in a matter of years as the wavefront moves across the field of Sagittarius star. This isn't the only piece of evidence that Sagittarius star has been substantially more energetic in the past. The famous discovery of the Fermi bubbles above and below our galactic plane suggests that some energetic event in the galactic center has been pushing gas out of the Milky Way. One explanation for this is a period of AGN-like activity in the past million years or so, but competing explanations about starbursts or a series of supernova are currently jostling around. Finally, we even see evidence in extremely high energy gamma rays that Sagittarius star may have been more energetic in the past. When we look at the galactic center above 100 TeV, so 100 trillion electron volt energies, we see emission coming from very close to Sagittarius star that might be the product of particle acceleration taking place close to the supermassive black hole. So by studying Sagittarius star in great detail, we can learn more about these past energetic events and build up a picture of our supermassive black hole, not just as a very low luminosity object like we see it today, but in the past as a more energetic object. And the X-rays we see with Chandra and CRISM are critical to that process. So besides studying these supermassive black holes with electromagnetic emission, I'm also a member of the IceCube collaboration, and several of the neutrino sources we've detected with IceCube, including the Seyfert galaxy NGT 1068 and a blazar flare from Texas 06, they're both neutrino sources in IceCube, and they're both supermassive black holes. And that means that supermassive black holes are kind of our leading candidate for studying neutrino sources and very high energy particle production in our galaxy. IceCube also detected a substantial neutrino flux along the galactic plane, including towards the galactic center. And while obviously Sagittarius star is much too dim today to explain all of that neutrino emission, we've just seen evidence in X-rays and gamma rays that Sagittarius star may have been much brighter in the past, both in electromagnetic radiation and in high energy particles that could produce these neutrinos. This is an ongoing topic of research, but one I hope that the next generation of neutrino observatories that are getting built around the world will be able to find in more detail, maybe by localizing neutrino emission from the galactic plane specifically towards Sagittarius star in that way. So we built up this picture of Sagittarius A star as today a very low luminosity AGN, despite having some flares, but that in the recent past could have been much, much brighter. Let's look further abroad now, further out into the local group, and see other galaxies that we can examine in this way. Sorry, summary slide. So the next candidate for looking at for supermassive black holes is the Andromeda galaxy, M31. Andromeda is a substantially larger spiral galaxy than the Milky Way, a few times larger in terms of stellar mass and dark matter mass. And correspondingly, all the relationships we expect between a galaxy and a black hole suggest that it should also have a more massive supermassive black hole. And that's been borne out by a variety of different modes of measurement. M31 star, the colloquial name for the supermassive black hole in Andromeda, is about 20 times as massive as Sagittarius A star, both by dynamical measurements and electromagnetic searches. Its X-ray luminosity is also much, much greater, and that means despite being 100 times more distant than Sagittarius star, it's possible to study M31 star in X-rays. We do not have quite as good constraint on the flaring activity of M31 star. I'll touch on that in a few slides in that way. When we look in towards the galactic center of M31 of the Andromeda galaxy, X-ray telescopes also provide an acute test of accretion onto M31 star, just like they do for Sagittarius A star. Because it's more massive, M31 star has a Bondi scale, a Bondi radius of about 1 arcsecond on the sky, which means that scale is resolvable with Chandra X-ray observations with an X-ray resolution below 1 arcsecond. And that means for M31 star, we can resolve the gas accreting directly onto the supermassive black hole at a variety of scales. Also, because we're looking towards the Andromeda galaxy from out of its plane, we don't have to look through vast lanes of gas, dust, and stars in order to image the supermassive black hole. We can peer down from above the disk and look directly towards M31 star. Obviously, M31 star is not an active galactic nuclei. Like I mentioned before, if it was, it'd be one of the brightest stars in the sky. But because we can study it in such great detail, because it's so close, and we can compare it to Sag-A star, we can compare it as a low luminosity galactic nucleus and investigate the supermassive black hole on that scale. Despite all of these advantages, the core of M31 star still has some challenges. Just like any core of a spiral galaxy, it has a bunch of other X-ray sources, mostly X-ray binaries in this case. And M31 star, unfortunately, has no less than 3 X-ray binaries within a couple arc seconds of it. And that means it's very difficult to extract a clean X-ray spectrum of the gas accreting onto M31 star without contamination by these brighter X-ray binaries. So in order to look at M31 star and learn about its history as an active supermassive black hole, we have to use 2D image reconstruction. And this is work that was started a decade ago using Chandra, and that I've continued in a recent paper with my collaborators today. You can see the two light curves we've constructed with Chandra observations stretching all the way back to before the turn of the millennium, looking towards M31 and reconstructing, using 2D image reconstruction, its activity. And we find a few interesting features that I think are illustrative of activity we can look for in other supermassive black holes or active galactic nuclei. First, we see occasional flares at about a 2% duty cycle. So about 2% of all observations have substantially larger X-ray flares, including this one we discovered in 2013. But then, most interesting, and this is an open question I'm currently working on, there was some very high luminosity event occurring in 2006 that we only caught after the fact, but seems to have dramatically changed how M31 is behaving in terms of its accretion. Before 2006, the X-ray radiation from M31 star was barely detectable. But after this very bright event, its quiescent X-ray flux increased dramatically so that it can be seen in even a short Chandra observation. Now, the fact of the matter is this observation occurred in a year-long gap in Chandra observations and was only caught after the fact. So sadly, we don't have follow-up information to know what exactly happened in this time period. But I think it says something very important about accretion onto supermassive black holes, both in active galactic nuclei and in low luminosity systems like M31 star, that an event like this can lead to a sustained change in emission rate. Doing a quick back of the envelope calculation, if we pretend that this is some tidal disruption event that led to continuous high energy emission over 20 years since then, it would take an amount of matter roughly equivalent to the moon to give you this amount of radiation. We don't know much beyond that about what happened to this event, sadly. So this event that we identified in 2013 was actually a very fortuitous, lucky find. I mentioned those three other nuclear X-ray sources that are buttressed right up against M31 star in the core of the galaxy. In this observation, they all happen to be in low states. X-ray binaries are variable as well, and we just got lucky in this observation that they're contributing very little contaminant photons, which meant we could extract a roughly 90% clean spectrum of M31 star from this particular observation. Now, it wasn't the longest observation, which means the spectrum is not great by X-ray standards, but it is something. It shows us a couple interesting results. First, the flare, which is highlighted here in red, wasn't accompanied by a dramatic change in the hardness ratio, the shape of the spectrum, compared to the quiescent level from M31. And even the flare back in 2006, when we calculated its hardness ratio, is also fairly typical for M31 star. This is odd, given we might expect that these dramatic flares be accompanied by the introduction of a new emission mechanism or a change in existing ones. Secondly, as you can see on the right, when we do extract the spectrum from this 2013 event, we find that it's still well fit by the traditional low luminosity AGN emission mechanism models in black and red here. So this flare in 2013, again, it's still a bit of a mystery. I think in particular, it would be great if future telescopes could have follow-up observations happening more quickly after these flares occur. Naturally, the event in 2006, if we had realized at the time that M31 star was 1,000 times brighter than it normally was, it would have been great to get other telescopes pointing at M31 star at that point. But failing that, we can only hope going forwards that our TDAM capabilities continue to improve. Finally, if the galactic center molecular clouds are present in M31 like they are in Sagittarius star, they could be illuminated by high energy emission from the supermassive black hole. Remember, M31 star is 1,000 times more luminous in X-rays than Sagittarius star, so these molecular clouds could be illuminated much more dramatically. Chandra itself is not sensitive to any single galactic center molecular cloud in M31, but it could possibly detect them if we sum up all their emission. Using a catalog of molecular clouds detected in radio, we see no such radiation being reflected off these clouds, which means we can put order of magnitude constraints on how bright M31 star has been over the past 1,000 years or so, obviously with big uncertainties about line of sight displacement. It is worth noting that New Athena's integral field unit combines spatial resolution and spectral resolution at the 5 electron volt level, which means it might be able to detect iron K alpha emission from these individual molecular clouds. The underlying point here, obviously, we only have non-detections at the moment, but Sagittarius star and M31 star are both dim supermassive black holes, but they're close enough and we understand enough about the galactic environment within a few hundred parsecs of the supermassive black hole, which means we can draw comparisons between multi-wavelength observations of nearby objects and the supermassive black holes themselves. And that's why these systems are so unique. So just to summarize, M31 star is 100 times more distant, but 100 to 1,000 times more luminous. We saw flaring activity much like we saw in Sagittarius star at M31 star as well. And that means that these two supermassive local supermassive black holes are useful objects to study as we look further out into the universe. And finally, there's still this mysterious event in 2006. We don't understand what happened, we don't understand what caused it, but some order of magnitude change in flux level has continued for the 20 years after that event. I would like to point out that if New Athena goes up in the sky, it might be able to see reflection from that 2006 event of those X-rays bouncing off these molecular clouds just in the next decade or so. So that'd be a very exciting thing to monitor for an M31 star. Let's wrap up this talk by looking at other local group galaxies. And this, I think, is really fascinating as an astronomer because we're used to interacting with numbers that are either in the billions or 0 or 1, right? It's interesting to be in a local group of galaxies where we can look at each galaxy as an individual and get detailed information about its composition. The Triangulum galaxy, M33, for example, appears to have no supermassive black hole in the center. That might not be surprising, it is a bulgeless spiral galaxy, but being able to put such strong limits on the non-existence of a supermassive black hole is fascinating. There's some work that suggests that the Large Magellanic Cloud, Hahn et al. 2025, might have a supermassive black hole ejecting stars from it, but multi-wavelength follow-up is needed. Specifically, M32, though, a small elliptical galaxy, it's a satellite of Andromeda, does seem to have both a central density spike and a possible radio and X-ray emission from a supermassive black hole with roughly the same mass as Sagittarius star in its center. And this is ongoing work that I'm hoping to get new observations from in the next few years or so, to revisit M32 in particular and try and find a third supermassive black hole in the local group of galaxies, increasing our sample of local objects to study by 50%. M32 is also a local elliptical galaxy, and both the other large galaxies in the local group are spirals, which means it's a useful environment to study the interaction between galaxy evolution and supermassive black holes at the local scale. Like I said, there's a coincident radio and X-ray source, which you can see here in a paper from 2016 from Yang et al. But that paper could not exclude a possible stellar mass explanation for this object, that it's an X-ray binary of some sort, or a microquasar, perhaps. And that's why I hope future observations with Chandra or other X-ray telescopes will be able to pin down whether this is the third supermassive black hole in our local group of galaxies. This is ongoing work that I hope can continue in the near future. So overall in this talk, I've talked about a few different case studies, examples of how local supermassive black holes and our knowledge of local galaxies with multi-wavelength observations can tell us about these big outstanding questions, whether supermassive black holes can be used as tests of general relativity and particle physics, and how supermassive black holes individually interact with their host galaxies. These questions have been studied in great detail on a population-based level, looking out into the wider universe. But our local supermassive black holes and our local group of galaxies is another way in which to investigate this in a very finely grained detail. Finally, I just want to point out that this work depends on X-ray telescopes. I talked a lot about Chandra and CRISM, as well as other telescopes like XMM Newton and NuSTAR. These are current missions which are pushing the boundary of being able to observe these very low luminosity galactic nuclei in X-rays. And I hope that future missions like Axis Lynx perhaps, or New Athena launching in the next decade, will be able to bring their capabilities to even further study these unique objects. So with that, I'm happy to take any questions or comments on any of these. You're welcome to reach out to me as email as well. And thank you for time to talk about my work at this Jamboree.
Hey, thanks. Thanks, Steve. So Travis has a question. So what is the velocity of that molecular gas flare in the bridge by the Sagittarius A stars?
Sure, yeah. So zoom back here real quick. Okay, the work I was doing with Chrism was on this molecular cloud here, G0.11, 0.11. And in X-rays, we were capable of constraining the radial velocity of that cloud to within the same precision as infrared and radio observations. For the bridge cloud has multiple subcomponents, each with a slightly different velocity structure. And so there are a lot of open questions right now that I don't think I'm qualified to speak about authoritatively about the 3D positioning and velocity of each of these clouds. Chrism's unique capability of R is equal to 1,000 energy resolution, which again sounds like kibbles and bits to optical and radio astronomers, but that's really amazing for X-rays. Lets us do these simultaneous studies in that way, though. So I don't think I'm qualified to talk about the bridge, but I know that G0.11 we can constrain even with just X-rays. It's a radial velocity.
So Shvala has the questions, so you can just ask the questions.
Okay. Okay. Hi, Steve. Thank you for the very exciting talk.
Of course, thank you.
Sure. The question that I had was, if you wanted to extend this kind of an analysis to beyond the local group, I'm just being very ambitious here, go all the way to the Virgo cluster, which has some of these really big, supermassive black holes. What does it take in terms of observatory?
Yeah. So I'm also a member of the high resolution the X-ray science the high resolution X-ray interferometry science working group in the X-rays. Sorry, garbled that a little bit. Extending our reach beyond the local group would require both increased angular resolution to the sub-arc second scales and even below. I know there are concepts talking about milli-arc second X-ray imaging, but also maintaining a high collecting area. I did a proposal in the Axis science book looking at how even just improved collecting area with Axis combined with arc second imaging, you would be able to resolve the different gas accretion temperature scales onto supermassive black holes outside of the local group, so nearby supermassive black holes. So an increase in X-ray spatial resolution while maintaining current capabilities would go a long way into extending beyond the local group in that way.
So would that still be within what New Athena can do, or?
So New Athena, I think for New Athena, I'm most excited for New Athena's capabilities for the integral field unit to be able to search for these molecular clouds around nearby supermassive black holes. And that, I think, I've only done the concept study for that for Andromeda in particular, because it's a galaxy I'm more familiar with. I think there's plenty of possibilities in galaxies with black holes with much, much higher X-ray luminosity that we could see molecular clouds throughout the entire galaxy illuminated in X-rays. So I've been only looking at molecular clouds in the cores of galaxies because the black holes I'm looking at are so dim. But in a black hole with a very, very high X-ray luminosity, that could illuminate molecular clouds throughout the entire galaxy. And New Athena would be capable of doing that even without higher spatial resolution like Chandra has.
Thank you. Very exciting.
So is there other questions from the audience would like to ask Steve? You can just raise your hand or post your questions.
I have a question.
Yes, please.
Since like the Chandra is giving a very good spatial resolution and the Grism is giving the spectral resolution, what type of joint X-ray analysis you have performed, and what are the models you used? It's a phenomenological models, or did you use any physical models?
Sure. I think you make a really good point about how X-ray telescopes can work in a complementary way to combine their different strengths in this way. So, for example, looking here towards the galactic center, the constraints on the layout, the 3D layout of these molecular clouds have emerged from XM, Newton, Chandra. IXPE has also made very tight constraints with its X-ray polarimetry measurements. Prism does not provide X-ray imaging at all. The image of an X-ray observation with Prism just looks like a big block of photons. So we have to be informed by high resolution imaging from other X-ray telescopes in order to create that model with Prism. But by combining the XMM Newton or Chandra model with Prism's observations and IXPE's polarization measurements, that's how we get this kind of multi-dimensional, very tightly constrained model for the galactic center. So it's all the X-ray telescopes contributing together to give perpendicular constraints on these models, I would say.
I mean, in SAG-A, it seems a very high diffuse emission as well. So how will you resolve this with the like disk emission or any other component that is also thermal?
Sorry, I'm not quite sure I heard the first part of your question. You cut out for a second.
Just by visually inspecting the Sagittarius images, it seems there is a diffuse thermal emission. So, like how we will distinct this thermal emission with the like disk emission or other Bremsstrahlung lung emissions. Yeah.
Okay, I think I understand your question. I think for Sagittarius star, which you're right, as an X-ray source is surrounded by other bright X-ray sources. There's a pulsar wind nebula right nearby, diffuse thermal emission as well nearby it. I think in that case, high timing resolution and looking at transient events is a good way to separate the fast variability we expect from an environment around a supermassive black hole with the very slow variability we expect from the larger scale system. And that's, I think, Grace's work on flares from New Star is, I think, a good example of how we can test both astronomical models and general relativistic predictions using these X-ray telescopes. I hope that answered your question. If not, please feel free to email me or reach out and contact me about that.
Okay, I think our time is up. We have to end today's talk. So tomorrow we have another two speaker. It's Pale Nandi from ESO and also Yang Sun from the University of Arizona. So I hope we can see everyone tomorrow. So thanks everyone to join Jamboree, series talk today. So thank you everyone and thanks to speakers today. Yes. So see you tomorrow.
Bye, everyone. Thank you.
Bye.